Today we will continue our discussion on beta decays. We will first consider the selection rules based on the angular momentum conservation. So, the process we are considering is beta decay, which converts an X type of nucleus to some Y nucleus with emission of electron and antineutrino, as discussed in the last lecture. So, let us consider the spins of these particles. The nuclear spins or the angular momenta, let us say angular momenta. Let me denote it by Ix, Iy, then the spin of electron denoted by Sc and S neutrino, plus there could be some orbital angular momentum, relative orbital angular momentum here. So, for the electron and neutrino system. First, let us consider the Sc plus S nu. Both of these are spin half particles. So, half plus half is equal to either 0 or 1 as per the angular momentum addition rules. L values the orbital angular momentum of the E nu system with respect to the Y say. So, to get an idea of what kind of L values are allowed or possible, let us consider some kind of a semi classical picture, where we could consider the nucleus as some kind of a spherical ball, and let us consider the case if the electron is originating at the center of this and moving directly along the radius, then it does not have any angular momentum L, because L is r cross p in the coordinate system. When you consider the relative angular momentum of electron, we are talking about the r, the position coordinate of the electron with respect to, so the position coordinate of the electron, let us say this is the case, consider this to be the center and electrons are emitted from the nucleus like this. In that case, r of electron is along the radius of this one of the nucleus, and L is r cross p, and p is now along the r cap direction, because it is moving along the r cap direction. So, that will give you L equal to 0 kind of this thing. But if it is not the case, if it is actually moving say tangential to this r, that is the case when r cross p will be maximum, and even the magnitude is maximum, the r perpendicular direction, the distance between the center and the direction of p, if that is also maximum, which is possible if the electron is emitted from somewhere at the periphery of the nucleus. So, in that case R is L is equal to basically R is now capital R, the size of the nucleus, times P, the momentum of this. That is the maximum kind of possibility. Classically, we are still in the classical picture. So, it is actually giving you some kind of an estimate, not an exact picture or exact values. Quantum mechanically we will have slightly different distance, but to get a feel of this thing we will take this kind of a picture. Okay. So, here R and P are perpendicular to each other. So, R cross P is just the magnitude, the product of the magnitudes R and P. So, let us consider the energy of the electron, say 1 or 2 MeV. So, let us consider a 2 MeV electron. Okay. So, we have the energy momentum relation which says P square C square is equal to E square minus m E square C power 4, right. And we have E to be 2 MeV, MEC is C square is 0.511 MeV. So, square of this is MeV square. So, this is the value of this in MeV square. It turns out that if you calculate this, do the calculation, P is equal to, I will leave the algebra calculation to you. P turns out to be 1.3 MeV per C, or Pc is equal to 1.3, square root of this, and then that is 1.3, and it turns out so that P is equal to 1.3 MeV per C. Now, L is equal to, or rather in quantum mechanics it is H cross L, which is the momentum, which is P, and L when it is taken in units of H is equal to PR, okay, is equal to 6 by 6. Let us see what is momentum. One is 1.3 into what is the value of R. R we know is equal to 1.2 in times a power 1 by 3 Fermi. So, if you take something like an A value around 100, 125, then you have A 1 by 3 equal to 5. So, let us say it is something like 5 will be approximately is equal to 6. So, 1 is exactly equal to 6 Fermi. So, we have 6 and units MeV per C divided by C coming from momentum, and 6 Fermi is the radius, nuclear radius. So, Fermi is coming from R. Now, L is equal to 1.3 into 6 divided by C is 3 into 10 power 8 meters. So, convert Fermi into meter, it is 10 power minus 15 meters, okay, divided by H cross. So, value of H cross is 6.58 say into 10 power minus 16 electron volts second and meter per second coming from C, and in the numerator we have MeV. So, let me write mega electron volt as 10 power 6 electron volt, and Fermi we already converted into meter. So, that is actually equal to meter. So, the units are the same for numerator and denominator, and therefore, as expected L is a dimensionless number. Okay. So, this is the angular momentum in units of H cross. So, this is, you do the algebra again and it turns out to be something like 0.04. Okay. So, that is a kind of a maximum expected value of the relative angular momentum of the electron coming from a nucleus, okay, a typical nucleus with atomic mass number, nuclear mass number A equal to something like 125, which is much less than 1, 100 times is less than 1 almost, and therefore, we expect that L value of the electron coming, the orbital angular momentum of the electron coming out is 0. Similarly, for the neutrinos, it is similar values 0, and then therefore, we expect L equal to 0 for most of beta decay. Or the other way of saying it is that the most probable beta decay, okay, it will have L equal to 0. If it is L equal to 1, although classically it is not possible the way we have discussed, quantum mechanically we can actually say that there is very less probability for this to happen. So, L larger than 0 will have small probability. Okay. In fact, the larger the L, the less likely it is as expected from this one, and one can actually have a more thorough rigorous quantum mechanical calculation, and it is also giving similar results. Alright, so now if we consider L equal to 0, which is incidentally called allowed decays, meaning L equal to 0, which is the one which is allowed by this one, and the rest of it L not equal to 0 are called forbidden decays, which actually means that they are less likely to happen, not completely forbidden. It is not a no kind of a situation, but it says that is very unlikely or to happen. There is one situation where this L equal to 0, even if it is energetically possible, it will not be possible from the point of view of angular momentum and parity considerations, and then it is possible to have, the only possibility is to have the forbidden kind of a decay. Okay. We will come to that actually in a minute. So, let us consider L equal to 0, and in L equal to 0, as already said, S can be 0 or 1. So, case 1, S equal to 0, the total spin of electron and neutrino combined. When S equal to 0, we have the angular momentum balance equation, the spin, nuclear spin I x, the initial nuclear spin I x is equal to I y plus 0. So, there is nothing to add. So, that actually says that both of these nuclei will then have the same spin, or delta I change in the nuclear spins of the nuclear, the daughter and the parent nuclei is equal to 0. So, this I is this, delta I is equal to 0, and then you can have a S equal to 1 case, and there I x is equal to I y plus S is 1 plus 1. To remind you again, this plus within the circle actually put in to remind you that these are not simple number additions, but rather it is the additions is according to the angular momentum addition rules, vectorial additions. So, this will tell you that actual number like addition, it is I y minus 1 the magnitude, I y plus 1. These are the possibilities. Here again, delta I is, if I x is equal to I y, then delta I equal to 0. If I x is equal to I y plus 1 or I y minus 1 magnitude, this delta is equal to 0 or 1 are the possibilities. So, it is possible to either have I equal to 0, delta I equal to 0 or delta is equal to 1 in the case of L equal to 0. A special case is 0 to 0 transition. Okay. So, this is I x is equal to 0 to I y 0 case. So, here delta I is equal to 0. So, it is only possible through S is equal to 0 transition. Okay. Only S is equal to 0 is possible. All other delta I equal to 0 case, it is possible to have either S is equal to 1 transition or S is equal to 0 transition. Okay. So, if it is S equal to 0 transition, we will call this a Fermi type and if it is equal to 1, we call this a Gamow-Teller type beta decay. So, Fermi type beta decay only means that S, the total spin of electron and the antineutrino is equal to 0, or electron and antineutrino are anti-parallel to each other, and Gamow-Teller type of reaction indicates that the spins of electron and neutrino are parallel to each other, thus giving S equal to 1 for this one. Okay. All right. Now, let us take some examples of the so let me write it first as a summary. So, allowed decay, which means L equal to 0, some terminologies, and pure Fermi. So, Fermi type possible delta I equal to 0 and 1, that is one thing. S is equal to 0 are called Fermi type beta decay, S equal to 1 are called Gamow-Teller type. Gamow-Teller type decay, and therefore, as 0 to 0, some cases 0 to 0 transition. Here I am denoting the I values of the x, and so I x to I y. Okay. 0 0 tells you that it is delta I equal to 0 and only possibility is S equal to 0. So, it is Fermi type. Okay. And if it is say 0 to 1 kind of a transition, then delta I is equal to 1, S is equal to either 0 or 1. Okay. So, it is delta S is equal to and that will be a mixed type. Okay. Then you can have 1 to 1, then that is delta I equal to 0 still, right. So, it is S is equal to 0 or S is equal to 1. Okay. So, then okay. So, I should correct myself. This is possible only if S is equal to 1, and therefore, this is equal to a pure Gamow-Teller type, and in the last case I is equal to 1, I x equal to 1 to I y equal to 1. This is delta I equal to 0, but S is equal to 0 or S is equal to 1, both are possible. So, we have actually both Fermi and Gamow-Teller types, or called the mixed type. All right. Now, let me come to the parities considerations. Parity of x is on the left hand side in the initial state, and parity of y times parity is a multiplicative quantum number, you multiply it to get the total resultant. Then you have the electron and you have the neutrino this thing, and you have the parity due to the orbital angular momentum, let us say L, which is equal to minus 1 power L. And if we are considering L equal to 0 allowed case, then, and we also know that P is equal to plus 1, P nu is equal to plus 1, and then therefore, that will give you P x is equal to P y. So, in this discussion, in the allowed decay, it is always P x is equal to P y. Okay. So, L equal to 0 will give you parity of the daughter and parent nuclei to be the same. Okay. So, that is one thing. Let us see what happens when L is not equal to 0. L is not equal to 0 are called forbidden decay, which are less likely. The probability for that to happen is smaller, less likely than the allowed ones, much less allowed decays. So, let us say case 1 L equal to 1, consider L equal to 1, and let us consider in that S is equal to 0. Okay. So, that will give you delta I is equal to, alright, let me take the angular momentum relation, I x is now equal to I y plus 1. Again, like earlier discussion, delta I is equal to 0 or 1. S is equal to 1 will give you L plus S equal to 0 or 1, and each of these cases let us consider separately. L plus S is equal to 0 will give you I x equal to I y, correct, or delta I equal to 0. Now, L plus S is equal to 1, that will give you I x equal to I y plus 1. Actually, L plus S can be 0, 1 or 2. I missed the 2 there. When you have L equal to 1 and S equal to 1, you can have L plus S is equal to 0, 1 or 2. So, anyway, so L plus S is equal to 1 will give you I x equal to I y plus 1, which is again delta I is either 0 or 1, and L plus S is equal to 2 will give you I x is equal to I y plus 2, that will give you delta I either 0, 1 or 2. So, in the case of L equal to 1, we can expect change in the parity, change in the I between the parent and the daughter nuclei to be either 0 or 1 or 2. Okay. L equal to 0 case, we had delta I equal to 0 or 1, L equal to 1 case, we can have L equal delta equal to 0, delta equal to 1 or delta equal to 2. Fine. Now, for L equal to 1, okay, what about parity? Is again P x is equal to P y times P times P nu bar times minus 1 power L, and as I said earlier, P is taken to be plus 1, P nu bar is taken to be plus 1. So, P x is equal to minus P y. So, L equal to 1, there is parity change in between the nuclear parities of the daughter and the parent nuclei. Okay. And fine, that is one thing. Now, let us consider calcium, 20 protons, take the isotope with 48 as the mass number. If we consider the beta decay of this, possibility is that it goes to scandium 2148 plus electron plus antineutron. Say, compute the Q value of this. Q is equal to, I will leave it to you to compute it. It is turns out to be 0.281 MeV. Positive Q value. So, energetically possible. Okay. But I value of calcium, IP of calcium 2048 is equal to 0 plus, and I scandium 48 P is 6 plus in the ground state. And if you consider the excited state, where still there is possible, it is possible to actually have positive Q value, it is still 4 plus and 5 plus, the first few excited states. So, for all of these, delta I is 6 ground state, 4 for the excited states, 4 and 5 for the excited states. Now, as for this, to get this, we discussed the L equal to 1 case, where we could get delta I is equal to 2, and to get delta I is equal to 6, you need L equal to 5. You can do the algebra exactly the same way as we did earlier. So, now L equal to 5 should be very unlikely compared to the case of allowed decay, or even L equal to 1, first forbidden decay kind of thing. Now, let us look at another possibility. Okay. Another possibility is that calcium 48 goes to not scandium, but titanium 48, which is having 22 protons in it. So, plus 2 electron plus 2 neutrinos. We are not saying that calcium first goes to scandium and then decays to titanium. That is not the case. It goes in one step to titanium, not as an intermediary, this one. Okay. In that case, if you look at the IP of initial, it is 0 plus, and Ti 48 has 0 plus as the ground state. Delta is equal to 0, it is an allowed transition, right. It will fall under allowed transitions. Here let us look at this reaction again. What is happening? We have a calcium NX nucleus going to a Y nucleus and 2 electrons and 2 neutrinos. So, this is not single beta decay, it is a double beta decay. So, these are typically called double beta decay, these ones, and we have other examples of double beta decay. So, let me call this the double beta decay, or sometimes also called beta beta decay. Okay. Let us take another example, say a germanium 76. It has IP equal to 0 plus, goes to arsenic 76, let us say, through a beta decay. That is a possibility. Possibility meaning that is the, if we consider the beta decay of germanium, single beta decay of germanium, then this is what will happen. 2 plus is the IP value of arsenic. So, delta I is equal to 2, no change in parity. Okay. It is actually a then forbidden. It is not possible even to have L equal to once decay, because L equal to 1 decay corresponds to a change in the parity. In this case, there is no change in parity. That is one thing. Even if we take the mass of germanium 76, which is equal to 75.921402 units, atomic units, and mass of arsenic 76, which is 75.922393 units, you see immediately that Q is equal to M germanium minus M arsenic. M germanium is smaller than M arsenic and therefore is smaller than 0 or negative. So, you have a daughter with larger mass, which is energetically not possible. You cannot have a particle to decay into a particle with larger mass larger than the parent particle, energetically not possible at all. So, from either of the accounts, anyway energetically not possible, we will not even need to discuss other things, but even if you consider the other whether it is angular momentum considerations, it is very unlikely to happen. But we can again consider the same germanium 76 and ask the question, what about the double beta decay possibility, SC76 and 2E plus 2 antineutrinos. Here IP is equal to 0 plus and 0 plus. Well, that is okay, and there is no change in parity. So, allowed decay. What about the masses? M SC 76 is equal to 75.919212 units, and Q turns out to be equal to plus 0.002190 U, whatever is the corresponding MEV is. We are not worried about the magnitude as such, but we will want to check whether it is possible energetically or not. So, which means that Q should be larger than 0, which is the case here. So, energetically allowed, no problem. Okay. The energetically allowed double beta decay with delta I equal to 0, which means and no change in parity, and therefore, it is an allowed it is possible to have an allowed decay. Again we have an example where it is not possible to have a single beta decay, but the double beta decay is possible. All right, very good. Now, there is another piece of topic that we would like to discuss under beta decay, which is basically the parity violation or parity violation in beta decay. Let us consider cobalt 60, which decays to nickel 60. In fact, it decays to one of its excited states plus E minus plus nu bar. I of cobalt is 5 and I of nickel is 4. Okay. Now, let us consider the situation where cobalt is prepared for the experiment. So, you take a large sample of cobalt and prepare it to be to have the spins, nuclear spins. This has a large nuclear spin I equal to 5, spin aligned to a particular direction, right. Perhaps most of the time, I mean, this is the way it is done using external magnetic field. Okay. So, if you do not prepare it in that fashion, what happens is that if you take a sample of cobalt, then its spin, although it has large spin, then if you have 10,000 of such or much more than that, even 1 mole of this 10 power 23 of these cobalt atoms, nuclei in it, and those all will be randomly arranged, and therefore, the total spin of the sample is equal to 0. But you can actually align the cobalt spin to be in the same direction by putting them or placing them in the sample in a magnetic field, which has some direction. So, the spins tend to align along the magnetic field, and then therefore, you get some direction for the magnetic field. So, that is what is happening. So, it is some kind of a polarized sample. Okay. So, let us look at, so that is what happens. So, we can actually arrange it and keep that in mind. Now, let me come to what happens under parity. For that, let us see what is spin. Say spin I, we denote the nuclear spin by I. So, let me consider it as a vector I. This is like the angular momentum, orbital angular momentum L. Okay, that is what we know. We will write L as R cross P classically, right. So, let us look at that. I mean, these properties remain the same under quantum mechanics as well. So, what happens under parity? What is parity? By the way, parity is the operation of inversion of space coordinates. So, in that case, the vector R goes to minus R, vector P momentum goes to minus P, which means that if it is moving along the positive x axis and parity operation reverses the direction of x axis, then with respect to the new x axis, it is moving now in the negative x axis. Okay. So, this is your x and something is moving in this direction, okay. And under parity, x will be reversed. Now, this is your new x direction, let me call it x prime, and p is, let us say, as far as that is concerned, this way of doing it, it is going in the same direction. So, effectively you can say p goes to under parity minus p. Okay. That is one way of looking at it. R goes to minus R, but L is equal to R cross P. Both R and P reverse sign. Therefore, this is going to be the same positive L, not negative. So, I also goes to plus I. Now, let us look at the cobalt 60 decay. Let us consider our x and y directions, all right, x and y directions. In the experiment, let us keep the cobalt so that the spin of the cobalt is aligned in the positive y direction, all right. And let us say there is an electron which is coming out in this direction in the third quadrant. Now, after the beta decay of the cobalt, it goes down to the nickel is there, nickel is also aligned in the same direction. So, electron is coming out in this direction anyway. So, this, let us see what would happen if we apply parity. Spin does not change under parity. So, we have actually under parity we will have x and y inverted, or effectively in an active picture we will consider it the parity acting on the vectors itself. So, cobalt spin remains the same in the same y direction, but electron has a momentum p, say the momentum is reversed, which means that the direction of emission of the electron is reversed now, which is the other direction, which is the direction which falls in the first quadrant. Okay. E is the electron with minus p now, because of the, if this is p, first one is p, then the new parity reversed electron will have minus p direction momentum. So, if parity is conserved, what will happen? If parity is conserved, we expect what? For every particle electron coming out in the negative y direction, as in the case of first figure, we expect an electron also coming out in the positive y direction, as in the case of second figure. So, finally, after some time, when we take say something like 10,000 such count some 10,000 of electrons coming, or large number of electrons coming out of such cobalt decay, with the spin of the cobalt aligned in a particular direction using the external magnetic field in an experiment, we expect, as if parity is conserved, okay, we expect number of electrons in the hemisphere with positive y coordinate is equal to number of electrons detected in the hemisphere with negative y coordinate. This is what we expect if parity is conserved in this particular kind of setup that we have. In fact, this experiment is performed. The experiment was performed to specifically look at this situation, and the experiment was performed by Wu and her collaborators. The result is that observation is that it does not happen so, okay, which means if you consider the number of electrons coming in the positive y direction and the number of electrons coming in the negative y direction, then this is violation. I mean, this is not the same. So, this says that parity is not conserved in such decays. Okay. In fact, parity is not conserved. There is a preferential. Electrons are found to emitted preferentially opposite to the spin of cobalt. That is the preferred direction for electron. Okay. It is not exactly opposite, but the distribution, if you take the y positive y and negative y, this one, it will happen. So, it is found that most of it is in the negative y direction. Okay. So, this is a parity. In fact, it is found that beta decay is confirmed to be a parity violating process. That is not the only process that violates parity. Okay. And there are other processes. In fact, beta decay is a weak nuclear process, and this is a new type of interaction, the weak interaction, and the weak interaction is a nuclear force, a nuclear interaction like the strong nuclear interaction, but they are much weaker than the strong nuclear interaction. Not only that, all of this weak interaction, including beta decay and other different type of weak interactions, all violate parity. We will come to more about weak interactions. Let me just write that. Weak interactions in general violates parity. Parity conservation is not possible under the weak interactions. We will stop our discussion of beta decay for the time being here, but we will come back to beta decay and the weak interaction in slightly more detail later when we actually discuss the particle physics part of the course.